Let's think about what it means to multiply 2 over 3, or 2/3, times 4/5 times 4/5. In a previous video, we've already seen how we can actually compute this. This is going to be equal to, in the numerator, we just multiply the numerators. So it's going to be 2 times 4, 2 times 4. And in the denominator, or we just multiply the denominator, so it's going to be 3 times 5. 3 times 5. And so the numerator is going to be 8, and the denominator is going to be 15. And this is about as simple as we can make it. 8 and 15 don't have any factors common to each other than 1. So this is what it is. It's 8/15. But why does that actually make sense? And to think about it, we'll think of two ways of visualizing it. So let's draw 2/3. So let's draw 2/3. I'll draw it relatively big. So I'm going to draw 2/3, and I'm going to take 4/5 of it. So 2/3, I'm going to make it pretty big. 2/3. 2/3, just like this. So this is 1/3, and then this would be 2/3. Actually, I could do a little bit better job making those equal, or at least closer to looking equal. So there you go. I have thirds. Let me do it one more time. So here I have drawn thirds. 2/3 represents 2 of them. It represents 2 of them. And one way to think about this is 2/3 times 4/5 is 4/5 of this 2/3. So how do we divide this 2/3 into fifths? Well, what if we divided each of these sections into 5? So let's do that. So let's divide each into 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I could even divide this into 5 if I want. 1, 2, 3, 4, 5. And we want to take 4/5 of this section here. So how many fifths do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we got to be careful. These really aren't fifths. These are actually 15ths, because the whole is this thing over here. So I should really say how many 15ths do we have? And that's where we get this number from. But you see, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Where did that come from? I had thirds, and then I took each of those thirds and I split them into fifths. So then I had 5 times as many sections. 3 times 5 is 15. But now we want 4/5 of this right over here. So this is 10/15 right over here. Notice that's the same thing as 2/3. Now if we want to take 4/5 of that, 4/5 of, if you have 10 of something, that's going to be 8 of them. So we're going to take 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. We took 8 of the 15. So that is 8/15. You could have thought about it the other way around. You could have started with fifths. So let me draw it that way. So let me draw a hole. So this is a hole. And let me cut it into 5 equal pieces, or as close as I can draw 5 equal pieces. 1, 2, 3, 4, 5. 4/5. We're gonna shade in 4 of them. It's 4 of the 5 equal pieces. 3, 4. And now we want to take 2/3 of that. Well, how can we do that? Well, let's split each of these 5 into 3 pieces. So now we have essentially 15ths again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we want to take 2/3 of this yellow area. We're not taking 2/3 of the whole section. We're taking 2/3 of the 4/5. So how many 15ths do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you have 12 of something and you want to take 2/3 of that, you're going to be taking 8 of it. So you're going to be taking 1, 2, 3, 4, 5, 6, 7, 8, or 8 of the 15ths now. So either way, you get to the same result. So one way, you're thinking of taking 4/5 of 2/3. Another way you could think of it is you're taking 2/3 of 4/5. We're now going to learn how to go from mixed numbers to improper fractions and vice versa. So first, a little bit of terminology. What is a mixed number? Well,
You've probably noticed that we've been talking an awful lot about fractions around here lately. Well, now I'm going to tell you something you can do with fractions that's really easy. No, not juggling fractions. Although that is pretty easy for me. I'm talking about something even easier than that. I'm talking about multiplying fractions. Multiplying fractions is super easy. In fact, it's easier than adding fractions, and that's why we're going to learn it first. The reason it's easier is because fractions are really just division problems, and multiplication and division get along much better than addition and division. Now, since fractions are division, that means if I have the problem 1/4 times 2/3, it's the same as the problem 1 divided by 4 times 2 divided by 3. That means I have both multiplication and division in the same problem. And because they get along so well, that means I can just rearrange our problem to look like this. Now it looks like two multiplication problems that are being divided, and it looks just like a fraction. In fact, if we go ahead and do the multiplications, 1 times 2 equals 2, and 4 times 3 equals 12, then we do have a fraction, and it's the answer to our problem. So what does all this mean? Well, it means that to multiply fractions, all you have to do is multiply the top numbers, and then multiply the bottom numbers, and ta-da! There's your answer. As always, let's see an example or two. Let's try this problem, 2/3 times 4/5. Now we could rewrite the problem like we just saw, but that's not necessary as long as we remember the procedure. First, we know our answer is going to be a fraction, so let's go ahead and write a new fraction line for it. Next, we multiply the top numbers. 2 times 4 equals 8, so 8's the top number of our answer. And last, we multiply the bottom numbers. 3 times 5 equals 15, so 15 is the bottom number of our answer. There we have it. 2 over 3 times 4 over 5 equals 8 over 15. See how easy that was? And fun, too. Even funner than video games. Okay, time for another example. Let's try 6 over 11 times 7 over 8. From our multiplication table, we know that 6 times 7 equals 42. So 42 is the top number of our answer. And on the bottom, we have 11 times 8, which is 88. So 6 over 11 times 7 over 8 equals 42 over 88. Oh, now some of you might see that this answer could be simplified, but we'll save simplifying fractions for another video. All right, let's see one last example. Here it is. 1/2 times 4 over 3 times 3 over 5. Wait a minute, this has 3 fractions multiplied together, and the middle one looks like an improper fraction because its top number is bigger than its bottom number. Does our procedure work for this problem too? Yep, all we have to do is multiply all the top numbers together, and then multiply all the bottom numbers together, and we'll have our answer. And this will work no matter how many fractions we have to multiply. So on the top, we have 1 times 4 is 4, and 4 times 3 is 12. And on the bottom, 2 times 3 is 6, and 6 times 5 is 30. That means our answer is 12 over 30. So there you have it. Multiplying fractions is easy because fractions are just another way of writing division problems. But remember, there's another way to think about fractions. We can also use fractions to represent parts of things, like half a pizza, for instance. But does it make sense to multiply half a pizza by another half? Actually, it does. If you're thinking of fractions as parts of something, then multiplying fractions is really like taking part of another part. For example, here's half a pizza. Now you can see that if I take 1/2 of that half, then I get 1/4 of a pizza. And if we do the multiplication 1/2 times 1/2, you see that we do get 1/4. So that's why you can think of multiplying fractions as taking part of another part. In fact, sometimes, especially in word or story problems, you'll see multiplying fractions written using the word of instead of times. They may ask, what's 3/4 of 2/3? And now you know they just mean, what's 3/4 times 2/3? So, whether you think of fractions as parts of something or as division problems, the procedure for doing the multiplication is exactly the same. Let's do a quick review of what we've learned. Multiplying fractions is even easier than adding fractions. It's easy because order of operations says that we can do the multiplication before the division. The procedure for multiplying fractions is to multiply the top numbers to get the answer's top number, and multiply the bottom numbers to get the answer's bottom number. If you think of fractions as parts of something, then multiplying a fraction by another fraction is the same as taking a part of a part. And sometimes, especially in word problems, you might see the word of instead of the word times. Even though multiplying fractions is so easy, it's a good idea to practice. So be sure to do the exercises, and I'll see you next time. Learn more at mathantics.com. In a previous video, we learned all about factoring whole numbers. And now we're going to learn how factoring can help us when working with fractions. We're going to learn how to simplify fractions. Simplifying a fraction means rewriting the fraction using the smallest top and bottom numbers we can without changing the value of the fraction. To help us understand what simplifying a fraction really means, let's take a look at the simplest fraction I can think of, 1/2. Now, this is already as simple as it can possibly be, so let's go the other way and complicate it by dividing our rectangle here up into more parts. The amount of our rectangle that's shaded is still the same, but now the numbers for our fraction are 3/6. The numbers are bigger because our rectangle is now divided into more parts. The fraction we have now, 3/6, is equivalent to our original fraction, 1/2. That means they have the same value. They represent the same amount. So what if someone gives you the fraction 3/6, like 3/6 of a candy bar? Well, we know from our picture that that means they're really giving you 1/2. But how can we show that using math and not pictures? Well, that's where factoring comes in. Let's take our complicated fraction, 3/6, and factor both the top and bottom numbers. Now, the bottom number 6 can be factored into 2 times 3. The top number, 3, is a prime number. Its only factors are 1 and itself. So we can write that as 1 times 3. There, we've rewritten our fraction using factoring, and now it kind of looks like two fractions being multiplied together. 1/2 times 3/3. Of course, 3/3 is what I like to call a whole fraction, since its value is equal to 1. Now here's the interesting part. Since 3/3 equals 1, and multiplying by 1 has no effect on a number, we can just get rid of that 3/3. Basically, the 3 on the top and the 3 on the bottom cancel each other out. And once they're gone, we're left with the fraction 1/2. So that means that the fraction 3/6 simplifies to 1/2. Another way of thinking about it is that we're trying to find any whole fractions that are hiding in the fraction we're trying to simplify. And if we find any, we can just get rid of them, and the fraction we're left with is simpler than the one we started with. Now that we know the basics, let's learn the procedure for simplifying fractions. First, replace the top and bottom numbers of the fraction with their prime factors. Next, look to see if any of the factors are the same on the top and bottom. If they are, then we call them common factors because they're something that both the top and bottom have in common. If you find a pair of common factors, you can cancel them out. Just draw a line through them, like this. And last, once all the common factors have been canceled, you need to remultiply any factors that are left over on the top or bottom. This makes sure that you end up with only one number on the top and bottom of your simplified fraction. Oh, and there's one important thing to remember. If you're ever able to cancel out all of the factors on the top or bottom of a fraction, don't be tempted to write in a 0. Put a 1 in there instead. The reason you can write in a 1 is because 1 is always a factor of any number. It's just we usually don't write it in. For instance, if you're going to factor the number 15, you just say that it's 5 times 3. But you could also say that it's 5 times 3 times 1. In fact, you could even say it's 5 times 3 times 1. See why there's always a 1 left over when you're canceling common factors? All right, so that's the basic idea behind simplifying fractions. And once you know the procedure, it's really not that hard. But you might want to rewatch this video just to make sure you've got the idea. Now, there aren't any exercises for this video because it's really just an introduction. But in part 2, we'll see a couple more examples of how you can use the procedure to simplify fractions, and then you'll get plenty of exercises to do as homework. Oh yeah. Welcome to part 2 of simplifying fractions. In part 1, we learned the procedure for simplifying fractions. Basically, you just take the top and bottom numbers and factor them down to their prime factors. And then you see if there's any factors that are the same on the top and bottom. We call those common factors. And if there are, you just cancel them out. And once you've canceled out all the common factors, you remultiply whatever's left over to get your final answer. In this video, we're going to see a couple examples of how we can use that procedure to simplify fractions. Let's start with an easy one. Let's simplify the fraction 5 over 15. Step 1 is to factor the top and bottom numbers. So, we know that 15 factors into 5 times 3. And 5 is a prime number, that means its only factors are 1 and itself. But 1 is always a factor, so we don't need to write that down. Step 2 is to look for common factors and cancel them. And we can see that there's a 5 on the top and there's a 5 on the bottom. They're not directly over each other, but that doesn't matter. They still form a common factor pair, and so we can cancel them out like this. Step 3 is to reorganize our answer. Now, we don't have any factors that need to be recombined by multiplying. We just have a 3 on the bottom, and we don't have any factors left over on top. But you'll remember that there's always a factor of 1. So 5 over 15 simplifies to 1/3. All right, I think we need to see another example, but a harder one this time. Let's simplify the fraction 30 over 36. The procedure is the same. Step 1 is we factor the top and bottom numbers all the way down to their prime factors. Let's do the top number first. 30 factors into 5 times 6. 5 is prime, but 6 can be factored into 2 times 3. So our 30 on top becomes 5 times 2 times 3. Now the bottom number. 36 can be factored into 6 times 6. And each of those 6's can be factored into 2 times 3. So our bottom number becomes 2 times 3 times 2 times 3. Well, it looks like we do have some common factors. There's a 2 on both the top and bottom that will cancel each other out. And even though there's more than one 2 on the bottom, we can only cancel one of them out because there's only one 2 on top. Remember, you always have to cancel common factors as pairs. Now we can see that there's another pair we can cancel. There's a 3 on both the top and bottom, so we can just cross those out. Okay, that's all the common factors we can cancel. So now all we have to do is see what's left over. We have a 5 on the top and a 2 times 3 on the bottom. We don't want to leave our problem looking like this, so we need to recombine any factors that didn't cancel. That means multiplying together our 2 and 3 on the bottom, which gives us 6. There, we're left with the fraction 5 over 6. That's the simplified form of the fraction 30 over 36. They both have the same value, but the simplified one is written using the smallest numbers possible. Now, some of you may have been taught that the way to simplify fractions is to find the greatest common factor of the top and bottom numbers and just cancel that. Basically, that's what we are doing when we cancel all of the common factors using our procedure. In fact, if you multiply all of the common factors together, you'll get the greatest common factor, or GCF as I like to call it, to sound cool. All right, so that's how you simplify fractions. But I'll bet some of you are wondering, why would we even want to simplify fractions? That's a good question. Basically, it's to make life simpler. Well, at least for your teacher who has to grade all your homework. For you, it, just makes life more complicated. No, just kidding. Simplified fractions make your life easier too, because usually simplified fractions are much easier to work with. For example, if your friend said to you, "Here, you can have 27/54ths of my sandwich," it would have been much easier if they had just said that you could have 1/2 of their sandwich, since 1/2 is the simplified form of 27/54ths. So now, whenever you see a fraction, you can ask yourself, could that be any simpler? And if so, you'll know just what to do. So get on out there, work on those exercises, start making the world a simpler place for us all. Learn more at mathantics.com. Hi, welcome to Math Antics. In this video, we're going to learn something called prime factorization. Wow, that sounds pretty complicated, doesn't it? But don't worry, it's not that bad. Now, from the name prime factorization, you can probably guess that it involves factoring like we learned about in the last video. But what about this word prime here? What does that mean? Well, to help you understand that, let's use what we learned in the last video to factor the number 7. Well, let's see, we could get 7 by adding 3 and 4, but factoring is not about what you can add to get a number, it's about what you can multiply. Well, since I can't think of any numbers that would work, let's find factors by testing for divisibility. Now, I'm going to do this really fast using my calculator. Let's see. Okay, here's the numbers I got. That's interesting. The only two numbers that didn't leave remainders were 1 and 7, and those are kind of obvious. We know that if you multiply any number by 1, you'll just get that same number. But why aren't there any other factors of 7? All right, here's why. 7 is a special kind of number called a prime number. Now, a prime number is just a number that has exactly two factors, itself and 1. There's a lot of prime numbers. Here's a list of all the prime numbers that are less than 20. 2, 3, 5, 7, 11, 13, 17, and 19. They're the ones you'll use most often. Now, some of you might be wondering why 1 isn't on the list of prime numbers. Well, 1 is a lot like a prime number, but for some technical reasons, it's not considered prime. Okay, so in a way, prime numbers are just special numbers that you can't factor. Well, unless you use the obvious factors of 1 and the number itself. But what's so special about prime numbers anyway? Why do we need to know about them? Well, prime numbers are like the building blocks of the other whole numbers. In fact, whole numbers that are not prime are called composite numbers because they're composed of primes. That means that you can get them by multiplying prime numbers together. Here's a good way to see how that works. Again, we'll list all the prime numbers that are less than 20. And now let's list all the composite numbers that are less than 20 over here. The first composite number is 4, and you get 4 by multiplying the primes 2 times 2. The next composite number is 6, and you get it by multiplying the primes 2 times 3. And the next composite number is 8, which you get by multiplying the primes 2 times 2 times 2. And the composite number 9 can be made by multiplying the primes 3 times 3. We could keep going like this, and you would see that all the composite numbers are made by multiplying different combinations of prime numbers together. And each of these combinations is called the prime factorization of its composite number. So the prime factorization is a thing. It's the set of prime numbers that you multiply together to get another number. That's true, but you can also use the term prime factorization as an action to describe how we find out what prime numbers a composite number is made of. And that's what we're going to do next. We're going to use prime factorization, the action, to find the prime factorization, the set of prime factors, for the number 12. And that just means that we'll continue to factor 12 until all the factors are prime numbers. Now, to do this, I'm going to use something called a factor tree. A factor tree is just a diagram that helps you keep track of multiple factoring steps. When you factor a number, you write the two factors below it with lines or branches going to them. And then, if you factor one of the factors, you do the same thing again. You'll see how it works as we do this example. So let's get started. 12 can be factored into 2 times 6. So we're done, right? Well, not yet. Because we're doing prime factorization, we need to keep going until all the factors are prime numbers. So let's see if they are. Well, we know that 2 is a prime number, but is 6 prime? No, it's not, because 6 can be factored into 2 times 3. And both 2 and 3 are prime numbers, so now we're done factoring. And if we bring down that 2 that we had from the first factoring step, we can see that the prime factorization of 12 is 2 times 2 times 3. Now I know what some of you are thinking. I didn't want to factor 12 into 2 times 6. I wanted to factor it into 4 times 3. Well, okay then, let's try it that way. This time we'll start by factoring 12 into 4 times 3. But remember, we need to keep factoring until all of our factors are prime numbers. So let's see. Are 4 and 3 prime numbers? Well, 3 is prime, but 4 is not. 4 can be factored into the primes 2 times 2. And again, if we bring down that 3 from the first step, we see that we have 3 prime factors for 12. and they're the exact same ones that we got the first time. That means no matter which way you start factoring, as long as you factor all the way down to prime numbers, you'll always end up with the same group of prime factors. Let's try just one more to make sure you've got it. Let's find the prime factorization of 42. Well, for the first step of our factoring, I see that 42 is an even number, so that means that we can divide it by 2 to get our first two factors. So 42 divided by 2 equals 21. So we can factor 42 into 2 times 21. Okay, 2 is prime, so we can't factor it anymore. But what about 21? Well, if you've memorized your multiplication table, you might recognize that 21 is one of the answers on it. You can get 21 by multiplying 3 times 7, so we can factor 21 into 3 times 7. And if you didn't remember that, you could have just done some divisibility test and you would have figured it out. Okay, so what about the 3 and 7? Well, they're both prime, so that means that we're done factoring. We bring down the 2 from the first step, and we can see that the prime factorization of 42 is 2 times 3 times 7. All right, now you know what prime numbers are, and you know how to use prime factorization to find the set of prime factors that a composite number is made of. And that set of numbers is also called its prime factorization, just to confuse you. As usual, it's important to practice what you've learned in this video so that you'll get good at it. And you can practice by doing the exercises for this section. Good luck, and thanks for watching Math Antics.